The next thing we're going to look at in this course is the concept of a force field. You've probably heard of force fields when it comes to like science fiction movies and things along those lines. Force fields in the real world, unfortunately, not necessarily as cool as what you've seen in movies, but they are, in my opinion, equally as fascinating, especially because we don't really fully understand as a species, as scientists, we don't fully understand where these force fields come from. Not all of them, anyway. So the three questions I would like you to be able to answer by the end of this video are: one, what is a force field? Two, how can force fields be visualized? And three, how can a force field diagram provide information about the strength of a field? So basically, what is a force field? How can I draw one? And how can I use that diagram to kind of help analyze this field? Those are the three things I'd like you to be able to take away by the end of this video. So let's get right into it. What is a force field? You've probably never thought about it, but when you let go of something and gravity pulls it down, or when you jump off of maybe a pool deck into the pool, the Earth certainly exerts a force on you and pulls you down. Two magnets. If you've ever kind of held a magnet in your refrigerator, you'll probably notice that you don't really need to actually have the two touching. Sometimes the refrigerator can almost pull the magnet out of your hand, despite the fact that they never touch. And static electricity. If you've ever pulled a t-shirt or maybe a sweater out of the dryer, you'll probably notice that it kind of clings to you. It might pull up the hairs on your arm. So these are three examples of a force field. So what actually is a force field? Well, you might not have ever thought about it, but each of these cases, one object was able to exert a force on another object, despite the fact that they never came in contact with one another. So a force field is apparently this ability for one object to exert a force on another without even making contact with that object. The more textbook definition is that a force field is a region in space around an object that describes the force experienced by a particle at that location. So, despite the fact that the Earth never needs to make contact with this apple, there is a region around space in which I can place this apple that apple will be pulled by the Earth. It will experience a force. Same thing with the magnet, and same thing with static electricity and the hairs on your arm, as an example. So, a region in space that kind of dictates the force or the direction an object will be pulled in, whether it's based on gravity, whether it's based on magnetic properties or electrical properties, that's what a force field is. You don't need to touch the object, or these objects don't need to touch a second object, but they can somehow exert a force over a certain distance. It's kind of freaky when you think about it, especially, as I said before, we don't really necessarily understand how all of that works. All right, so now that we understand what a force field is, how can force fields actually be visualized? How can we draw them? How can we analyze them? And we do that with what's called a field diagram. A force field diagram is just a visual representation of the forces experienced by a particle, and we use arrows to represent what's going on there. I think the easiest way to look at it would be to look at the example of gravity, because I think that's one thing that most of you are familiar with. So it's important to realize that gravity is based on mass. It's the it's the attraction, the force of attraction between any two masses in the universe. So in the classroom, we assume this is the ceiling and the floor. If I took a mass and I held it at any of these locations and let go of it, you'd hopefully realize that the Earth is going to force these objects to move downward. It's going to exert a gravitational pull that will move these masses downward, no matter where in the classroom I place it. Now, if I zoom out and look at the Earth, it's a little bit different. No matter where I hold these masses, the Earth will certainly attract these masses, but it's going to try and pull them towards its center. So if you think back to like third grade, you may have wondered, okay, well, if I stand up here, obviously I fall down, but how come, I don't know, people in China or in Australia, how come they don't fall off of the Earth? And that's because gravity is the attraction between two masses trying to pull one another towards their center. So each of these masses will get pulled towards the center. Now, if you notice that all of these masses are getting pulled down and all of these masses are getting pulled towards the center, well, the only other thing we need to realize is that field lines in these diagrams, they just represent the direction, in this case, since it's gravity, that a mass would be forced to move. If you look at the classroom, all of these masses will generally have a downward force exerted on them. And in the case of the Earth, each of these will have a force exerted that pulls it towards the center. So it's not too much of a stretch to realize that the actual gravitational field in the classroom looks more like this. whereas the gravitational field around the Earth looks more like this. And in either case, these field lines represent the direction a mass would be forced to move. No matter where in this classroom I place a mass, it will be forced to move in this downward direction. Just like on the Earth, no matter where in the space around Earth I hold a mass, once I let go of it, it will follow the direction of these lines, and that is the direction of the force of gravity that will act on it. So these field lines, in any case, just represent the direction that an object will be forced based on whatever field you're talking about. Since it's gravity, we're talking about masses. Any masses placed in either of these locations will follow these lines, and that's the force they'll experience at that location. A second case would be electricity, which is based on electric charge as opposed to mass. So in this case, if I had a positively charged plate and a negatively charged plate, well, if I placed a bunch of positive charges, hopefully you realize that positive and positive, like charges repel, opposites attract. So this guy will be repelled by this plate, attracted by this plate, and he'll be forced downward. Whether I place him here, here, or here, in all three cases, he will be repelled by this top plate, attracted by the bottom plate, and therefore, it doesn't matter where I place this positive charge will always move in a downward direction when placed between these two plates. Similarly, if I place a negative charge and choose any location in the space around it to locate a positive charge, that positive charge will be attracted and will be pulled towards the negative charge's center. In this case, the field lines represent the direction a positive charge would be forced to move. Not a mass. The mass is what's based on gravitational fields. Electrical fields are based on the direction a positive charge would be forced in. So similar to what we did before, if I represent these electrical fields, you'll notice that the electrical field between these two plates is moving in this downward direction, whereas the electrical field around this negative charge is going to be looking similar to this. And that's just because these field lines represent the direction a positive charge would be forced to move. Now, the very last thing I'd like to look at is how can a field diagram provide information about how strong a field is? So what I'd ask you to take a look at is this diagram on the side and realize these two questions. What happens to the force of gravity, also known as the weight of an astronaut, as they move further from the center of Earth? And while you think about that, from whatever you know about movies or documentaries you've seen, I'd like you to also think about what do you notice about the field lines relative to one another as they move out away from the source. So as an astronaut moves further from Earth, what happens to his weight or his force of gravity? And what do you notice about the field lines relative to one another? And I've drawn in D1 and D2 in order to give you an indication of what I'm looking for. Hopefully what you started to realize is as an astronaut moves further from Earth, that astronaut's weight decreases. The force of gravity lessens the further you get away from Earth. You'll hopefully notice that the spacing between these lines increases as you get further away from your source, in this case the Earth. So it's not too far of a stretch then to realize that the field line spacing provides the strength of the field at any given location. The larger the spacing, the weaker the field, and the smaller the spacing, the stronger the field. So it's clear to see here now that when I'm closer to the Earth, because I have a smaller spacing, this field strength is stronger and there's a stronger force of gravity. As I get further away, the spacing is much wider and therefore the force of gravity is much less. Now, this is not the reasoning for this. This is just a visual representation. We'll get to the mathematics behind why this is the case, but when drawing field lines, field diagrams are a very, very, very good way to take a look qualitatively without numbers of analyzing the strength of a field at any given location. And it's simply done by taking a look at the spacing between those field lines. So hopefully at this point you have a better idea of what force fields are and you're able to answer these three questions. If you're not, certainly call me over or review the information in this video again, but these are the three questions you should feel comfortable answering before moving on with the activity.